Hello guys, thank you so much for being with me in another machine learning tutorial video. We said in the previous video that we already had an input layer and an output layer. Now in neural networks we have one or more hidden layers that are hidden from the outside world. The feature of these layers is that each element of the input layer is connected to the elements of this layer. So this layer can learn whatever it needs by itself. After applying functions to the raw inputs, we arrive at a new set of features. These features are a combination of lower level features. That is, they are higher level features. For example, in image recognition, raw features are pixels and higher level features are lines and geometric shapes. We call this hidden layer H. Now we have to calculate the points from the H layer and its features. We call this network a two-layer neural network. One layer is the hidden layer and one layer is the output layer. These are fully connected neural networks because each input element is connected to all the elements in the next layer. This network can also be called a neural network with a hidden layer. We can apply another nonlinear transfer on the features of the same hidden layer and reach the high-level features. It means to add another hidden layer and calculate the final scores based on the features of this layer. If we increase the number of hidden layers, we reach deep neural networks. To be more precise, these are called MLP, multi-layer perceptron. If we want to review the calculations, we already had an W matrix. We would multiply it at the input and add it with bias. But now in two-layer neural networks, one layer has been added to the calculations. We must apply a linear function, which is the activity function to the previous calculations and then calculate the scores. For this calculation, we must multiply the secondary features by the result of the previous transfer and add it with the second bias. If we look carefully, the calculations are very similar. Implementations are not difficult. I have provided you with the relevant codes in the files. Here I have defined the activity function first, and then I have generated the input random vector, then we have created two hidden layers, and finally we have calculated the points from the last layer. So the only difference is that instead of calculating the scores directly from the input, we do the calculations layer by layer. We call this stage forward stage in neural networks. In the neural network training phase, we also have a backward phase. Here the numbers from -1 to +1 are considered. Here we have generated 4 higher level features from two features x1 and x2. Then we have produced 2 higher level features from these 4 features. Classification based on these last 2 features is much easier. The thickness of these ridges indicate the weights. A linear classifier cannot detect such a boundary. There are other examples where the data is arranged in a spiral. Refer to the address available in these files to practice more and more. Now, if we don't have these nonlinear functions in the hidden layers, for example, instead of fx, we put the function. For example, fx is equal to x. These f's become the same function. I mean the y is equal to x. According to the participation feature of matrix multiplication, we can name this matrix product W. So if these activity functions are not nonlinear, our neural network becomes a simple linear classifier. The sigmoid function is no longer used as an activity function. An alternative function that is very similar to the sigmoid is the hyperbolic tangent function. Unlike sigmoid, this function has outputs in the range of negative infinite, and positive infinite, and is a bipolar function. The hyperbolic tangent function is mostly used in texts. ReLU function is used in image recognition. This function is the same function for positive x and is equal to 0 for a negative x. It means that for positive x's, the ReLU function works as same as the y is equal to x function. The results of recent research show that by replacing a hyperbolic tangent with sigmoid, the training speed increases 6 times. If you are interested in learning more about neural networks, you can download the package for this lesson. The main name of these networks is artificial neural networks, the natural neural networks that exists in our brain. But the neural networks of our brain are much more complex and continuous than artificial neural networks. This difference is complexity. This difference in complexity is so great that these two networks cannot be considered similar at all. Different sciences aim to understand the brain. In artificial intelligence, we also want to know the brain, simulate its networks, but it is not really possible because these artificial neural networks are much simpler than natural neural networks. Our brain is made up of 100 billion neurons. Each neuron is a simple computer for itself, that there is a network of these neurons. The input of each neuron is the output of other neurons. On average, each neuron in the brain is connected with 10,000 to 50,000 other neurons. And the received signals are collected in the nucleus of the neuron. If this contraction exceeds a certain limit, this signal is sent to the output by the axon and goes to other neurons. At the output, there is a gap called the synaptic gap, where the signal changes its nature a little. This change depends on many parameters and our experiences. Of course, this explanation has nothing to do with the applications of artificial neural networks. These explanations are presented to you only to familiarize yourself with the discussion. This is similar to what our artificial neural networks do, because these networks are very simple models of natural neural networks. These neurons in neural networks somehow follow hard limit functions. Now, a neuron alone is not powerful. The power of the brain comes from the parallelism and sequence of those neurons. We have also tried to follow the example of the brain in order to achieve high efficiency and power in problem solving and learning by layering these networks. But these very simple models solve very high level problems in the world. This idea started in 1942. Until today, we have reached the heyday of neural networks. Now, how effective are these neurons and the number of layers? The more layers you add, the more complex the function representing our decision boundary will be. The problem is transferred to a higher dimensional space, which makes classification easier, but the problem of overfitting may still occur. So here we should use regularization, and the first time we discussed a regularization was when the number of features is large. But if we want to minimize the number of neurons, we will reduce the efficiency of the network. It is suggested not to use the number of neurons as a regularizer. Rather, let the number of neurons increase as far as the calculations allow the increase of neurons, and then solve this overfitting problem with a regularization. But the training of neural networks is not much different from what you have learned so far. There is an algorithm called the error backpropagation algorithm that is used to calculate the decreasing gradient. For your review and understanding, here is a calculation graph for you. This is the forward propagation, and this is a back propagation. What we have done is taking the differential of this L with respect to these W's. We have also used the rule of chain differentiation. This is the idea of backpropagation. Many people mistakenly think that this algorithm is for training neural networks, but the application of the algorithm is only to calculate the gradient. Next, we use these gradients for updates. We have two layers here. We consider a weight matrix for each layer. We calculate the differential of L with respect to S, and then we also calculate the differential of S with respect to W2. That is, we use the same chain rule. We must continue the same work in other layers. If we know the steps ahead, the work here is very simple. As you know, we can combine bias with weight metrics, so we can ignore this bias here for simplicity of calculations. If we multiply the differential relative to the output by the local gradient, it becomes the differential relative to the input. These input themselves may be the output of previous layers. Finally, if we want to see the implementation of neural networks, first we calculate X, W1, B1, and A, and H in the forward calculations, and then we calculate the points by having H, W2, and B2. Now we calculate the cost function. Now that we have calculated the loss, now we enter the backward stage, and we have to calculate the differential of L with respect to W. Here D score means DL divide by D score. I have written this way for convenience. We get the gradients and then we start the updates. Here is a summary of the backpropagation. For you, but we can also use advanced optimization methods. We can always replace these methods. These methods with gradient descent algorithm, we have already said that the implementation of these methods exists in the SciPy library. In this code, we have to implement J ourselves. The X's are the W's that we need to initialize with small random values. The arguments are the training set. CG is a method, and the jack are the same gradient. This means that this cost function returns both costs and gradients. In this way, many redundancies are avoided. And there is a problem here. W0 is a vector. If we have a lot of matrices and vectors here, we have to combine them all and convert them into vectors. I have given you examples in the Python files, which I suggest you pay attention to them. I again highly recommend you not to miss the upcoming lectures because of the very practical and important tips inside them. Have a nice time.